I decided to talk about data visualization a little bit first. And then the second half, we'll talk about how to draw simple plots, or we're going to cover some fundamentals about data visualization in Python, specifically Matplotlib library, which has a lot in common with the way you do visualization or plotting in MATLAB. Then next class, I'll talk more about different types of plots. And after that, which is going to be the 2 weeks from now, will be, I'll try to talk about more advanced visualizations, how to make more interactive, I would say fancy plots, how to do plotting when it comes to maps, how to identify points on a map, draw a map in Python, an interactive map. Different types of, I would say, more advanced plots. We'll see how it goes. Learning how to communicate is a complicated thing. You have to take courses, you have to actually practice a lot. But one of the factors in communication is, at least for scientists and engineers, is how do we represent our outcomes? And that's where data visualization comes into play. How do we get people to understand what we found? We have to be able to communicate. We have to be able to keep people engaged. Now, again, one step in that is to be able to visualize the data, visualize the outcomes we get. The first thing we have to answer is, why data visualization? Right? Why do we visualize the data? You might have some answers in mind. I found something, I want to show it to other people. I want to communicate the result, as I said. I want to, one of the important, I wouldn't say important, but newly focused areas is telling a story using data, which is a very, I would say, interesting field or area that I also personally like it. Because finding things is one thing, or visualizing it or having the result is one thing. Telling a story using what you found is a different story. Right? Storytelling is a skill. It's something that involves data visualization, good graphs, and correct presentations for the type of data or for whatever you want to communicate. But it's a whole new I wouldn't say field, but it's a whole new area of interest that, if you're interested, I would highly encourage you to look into it and learn more about storytelling with data and with results. It can help you a lot in the future in your career. Focus on that. Try to develop your soft skills, especially presentation skills and storytelling. You're telling a story. You have to convince your audience. Keep in mind that the project itself is not the goal. The project is a means, is something that takes you to goal. The goal is, in business, is to convince the client that you did the right job, is to convince your supervisor or manager that this is the correct result, this makes sense, or this is what we have achieved and it's valuable. Right? So you have to be able to communicate. Now, data visualization, right, is one step towards that. Now, the first the first thing that data visualization can help with is exploratory data analysis, right? In data science, away from the communication story. In data science is exploratory data analysis. Now, when you get a data set, right, the first thing you need to do, you have to understand how things change. What are these variables and how do they change versus one another, or if there is any specific trend or pattern in your data. And the easiest way to do it is by making graphs and plots. Using data visualization is what I'm trying to say, is something that is going to help you a lot. Now, obviously, it's much better and much easier than just looking at a set of data and trying to find out if there is a pattern. A very simple example would be, if you think about it, when you draw, let's say you have a data set and you draw two variables, and you try to figure out whether these variables have any relationship. Right? I'll just call them X and Y. It can be anything. It can be time versus specific variable changing your experiment, right? Or two variables changing your experiment. Depending on what you get, can be you might plot this and visualize the data, and you realize that, oh, there is a relatively linear relationship between these two variables, right? These two specific parameters in my data. This is something that you can't easily see or figure out by just looking at the data, right? Visualizing it easily is going to tell you there is obviously a pattern there. Or, you know, if you, it might not even be a linear pattern, right? It might be something that you feel like, oh, I feel like it's some kind of quadratic relationship or some kind of polynomial relationship between these two data. This is the simplest thing that I can think about. So there's a pattern there, and you can easily see that once you visualize the data instead of looking at just numbers. So once you get the data, you will see when we talk about exploratory data analysis, one of the first steps we do, not like the first step, is to plot. You know, we look at the statistics related to the data, and also we plot the variables and see how things are changing. Right? The next thing, error detection. Right? So when you get your data, right, again, in terms of data, when I talk about data, I'm talking about measurements in the scale of tens of thousands of measurements. Right? Let's say you're measuring the temperature or a specific parameter every 5 minutes in a span of 10 years. This is a lot of data. It's not something that you can look and figure out, oh, there is a problem there, or there is an error, or there is an outlier point. These are situations that you can only see these problems if you plot the data. And again, following that example, if you think about measuring some parameters, right? Let's say you're measuring temperature for some specific experiment. And for instance, the data, let's call this temperature, and or let's call this time, right? Days, minutes, weeks, whatever is the unit for time you have. And let's call this temperature. Right? You're measuring the temperature, you know, during different phases of the experiment. You know, for instance, temperature, like environment temperature is 20 degrees, environmental temperature, and you know you're changing it just a little bit, so the data points you're getting are, you know, around this 20 degrees, maybe a little higher, a little lower, depending on how your system works and whether you are increasing or decreasing the temperature for your system. But then suddenly in the middle of data, when you plot it, you see one data point that is right here. Right? It's, for instance, not into scale, for instance, 500 degrees. Now, this is an outlier. This could not happen. Obviously, the environmental temperature for that experiment couldn't be 500 degrees. So once you plot this data, you immediately see this error. You immediately see that there is something went wrong there. Now you can go look at it and see when did that happen. Let's say at week 2nd of the experiment, this temperature, weird change in temperature happened. And I want to know why. Then you can look further into what the problem could be. Could be a sensor malfunctioning, right? Something that you were measuring and the sensor suddenly had some error in it, or it stopped working, or it sent the wrong signal. Could be a coding problem, or the way the program was interpreting the signal coming from the sensor. Anything, or it could be a legitimate. There could be a legitimate problem. Instead of 500, maybe it's 50 degrees. And you realize that, oh, at that specific moment, someone used a LiDAR next to your experimental setup and the temperature suddenly went up. Can be any of these, right? Then once you know there is the reason, or at least you have a guess of what the reason could be, you can decide whether you're going to eliminate that point, or you are going to find a way to incorporate it into your results. Right? Or maybe one other thing would be you realize that you made a wrong assumption about the experiment, right? Let's say instead of having the temperature around 20 degrees, the temperature starts around 20 degrees for your experiment, and then suddenly it goes up, right? It keeps going up. by looking at this plot, you realize that, goes up and then comes back and keeps fluctuating around 20 degrees. By looking at this, you realize that, oh, there is this specific parameter that is affecting the experiment, and I didn't take that into account when I was making an assumption about this experiment or this process that I was doing to study a specific characteristic of a system. Right? So it can help you to actually modify your assumption. If there's an error or the assumption you made or some parameter you missed, take into account. So the last thing that data visualization can help, if I can, oh, I know why it is. Okay, the last thing that it can help is communication, as I said. Right? Probably I should have put it at the top. You have to present your results effectively. As the famous saying, like, a picture is worth than 1,000 words. Like, when you have a good plot, if you have a good presentation, that is going to tell a good story, way better story than showing so many numbers and results that you got from your simulation or experiment. Again, that goes a long way. And keep in mind that by communicating effectively and data using proper graphs and plots, you can tell a good story. Storytelling, again, is a great skill. So you start from somewhere, you use these data visualizations to tell what happened, why happened, and whether it should have happened or not, and what conclusion you can make based on what happened and what should have happened or should not have happened. So keep that in mind. Not within the scope of this course, but I highly encourage you to really work on your communication skills. And data visualization is going to help with that. So these are three main things that, at least within the scope of data analysis and data science, these are the main things that why we care about data visualization. Right? Exploratory data analysis, error detection, and obviously communication, effective communication. Now, what type of chart should be used? This is a very also important question to ask, right? I've seen so many bad charts, right? And I've made so many bad charts myself. I'm not safe also in this area. I am also prone to error. So I keep reminding myself, what is the best way to represent the result that I got? You can't just plot something versus something and say, well, this is the result, right? Your graph, again, for 10th time, should tell a story, should say something, should say whatever you want it to say, right? You have a purpose, and that visualization should help you with that purpose. If it doesn't, then you have to change it. Now, there is a general rule of, I don't want to say rule of thumb, but a general approach to at least a good way to think about what kind of chart you have to go for. Helping you with the process a little bit. I put it here. I put the reference there. This is a relatively good, I would say, classification of what type of chart you should think about, depending on what type of data you want to represent. If I zoom in, some of these, I put the reference to original PDF, so you can always click on that and print it for yourself. Few things, right? If you want to represent, see, the main question is, what would you like to show? If you want to show a relationship, right? And there are two variables that you want to show the relationship. It's the most common one, you all know that. Right? If you want to represent a relationship and we have two variables, so we'll easily just plot variable 1 versus variable 2, right? Typically we use a scatter plot. When we have data points, we use a scatter plot to show how they're changing. In this case, you see it might be a linear relationship between these two variables. If there is more than 2 variables, stopping at 3, usually it's not suggested to through so many variables in one plot. We might do it later on when we talk about Python and how to plot things. I'll show you how can you do it if you want to, but typically in terms of communicating and making it easier for the audience to follow what is going on, we keep it at 3 variables. Right? And this is a bubble chart. I don't know whether you have seen it or not. I'll talk about it a little bit when we go further, but I will talk about different charts. But pretty much same as a scatter plot, right? You still have your variable 1 and you have variable 2. You plot them against each other. Now you're going to use the size of the data point as the third variable. Let's say time is changing versus some variable you're measuring, or two variables are changing. Stress and strain are changing. You're doing some tensile testing process on a material. Stress, strain are changing, and you have some data points. You want to show something else on top of it. You want to show the type of material. Right? These are assume that these are average values or a specific point. Let's say specific point, right, on that plot. And you want to show the third variable as what the material is, for instance. Maybe that was not a good example. I have to think about a better example. But the idea is you have two variables, and the third variable is going to be the size. So the higher that magnet or that value, the bigger these bubbles. The small bubbles show small values, large bubbles show large values. And you're going to give a scale that, you know, the area of the bubble is obviously related to the value of that quantity you're trying to represent. So by adding the size to those data points, you create a bubble chart and you represent three variables. Another example here, I'm not going to talk about all these plots. Another example here would be, let's say, distribution, for instance. You want to show the distribution. If you have just a single variable and you have few data points, you know, use a simple histogram. Right? Although we do not exactly, the lines are blurry between few data points and many data points, we still use histogram, even for many data points. But generally speaking, column histograms. But generally speaking, you can use a histogram to show how the variables are distributed. Right? Two variables distribution, you can still use a scatter chart. Three variables, you know, you can use 3D plot. Not very common, and suggested 3D plots are less common in data analysis. Of course, in engineering, we use them a lot, but in data analysis and data science, you barely see 3D plots, at least from what I know. Other plots, if you want to make a composition, right, changing something over time, if you have few periods, right, let's say you have, I'm talking about this part, right? I want to make a I have a composition, changing something over time, and I only have few periods. Let's say I want to show the amount of rain in different days of 1 week. I can just use a simple column chart. Now, depending on if you want to show the relative distribution, you just scale them all to 100 and then plot them next to each other. So people can see that, oh, this variable, whatever it was, right, now it's less in terms of its proportion with respect to all three variables that we're measuring. It's increasing a little bit, and now it's pretty much still the same in terms of its portion with respect to other variables. Right? Everything is stays at 100. You can just stack them together and don't show the proportionality. Maybe you care about the absolute values, so you just put them together. Now the top part changes, right, depending on how they change. So it's not relative, it's absolute. It helps. It's relatively easy to follow the change in a variable, right? Over, if you have just few periods, 4 or 5 periods that you're measuring, again, days of a week, 1 week, or months of 1 year, so just 12. Now, if you have many of them, it's easier to just use area chart. I'll leave it to look these charts up. There is a lot here that I can pretty much spend the rest of this class just talk about every single chart here. But this is a good general guideline. Tell you what you want to say first. What is the purpose of your graph? And then gives you general direction. Okay, so what should you look into? what kind of plot you should use. All right. Now, one thing before we even talk about graphs is a very common way of representing data that I did not put here is to use tables. We still use tables a lot. It's not like they're outdated. We love graphs and plots, but tables are still necessary to represent different types of data, right? Especially if you have a kind of data that has so many features, like you're measuring so many parameters over time. Let's say you're measuring something every hour, you're measuring 20 things every hour for 1 year or for 1 week. You still need tables to represent this data. So let's talk a little bit about tables before we dive into a few common charts and plots. All right, so tabular data, a couple of advantages they have. Again, as I said, this is the era of graphs, visualizations, animations, interactive visualizations and graphs. It's great, but we still need tables. A couple of advantages tabular data has that you cannot find, or it's hard to find the equivalent in graphs. You might need multiple graphs to actually represent whatever just one table can represent. From the top, the first thing is precision representation. Right? When you plot things, there is a limit to how precise you can give the number. Right? Usually, you can add more, let's say, ticks to your label, like Y label, X label. Say this is the interval is 0.1, 0.01, and then you plot the data, but you can't give the exact value for each data point. Right? That can easily be done in a table. When you have a table, you pretty much can represent the data, right, with any decimal point as accurate as you want. Right? 12.567. The next value can be 10.052. The next value can, go on. So you can give a precise representation. The second thing is scale representation. What does that mean? It means when you are writing the values in a table visually, let me put it this way. Visually, it's easier. For instance, I'll put the, I don't know, let's say price of something. Engineering term, let's say stress on a specific part on your system. Visually is easier when you put the numbers. Let's say the price of the first thing is $2. Then the second thing is $100. The third thing is $20. I don't know why I'm using two. One thing can be $5,000. Right? When you look at this, it's kind of easy to, it's easier to compare these values. Now, I'll talk a little bit about how to align the different types of data in a table. You can represent multivariate visual. You can have a multivariate visualization. That's what I was trying to say before. So if you have a table like this, you can represent so many parameters. You can represent 10, 50, 20, 30 parameters. This can be, again, in terms of engineering, this can be a stress, this can be a strain, this can be von Mises stress, this can be deformation, this can be, it can go on and on for one specific point on your, let's say, finite element result structure. Sorry, the result of your finite element analysis. So there is almost no limit to how many variables you can represent for any given, or how many features you can represent for any given data point. So it's multivariate. It provides you with a multivariate visualization. Last thing, you can represent heterogeneous data. Like heterogeneous data, you can represent names, values, floating numbers. We can use integers. categories, like if you're presenting something about different countries, you can put the name of the country in one column, population of the country, which is a number, in a different column. You saw it when we were talking about pandas, like how to import the data and put it in a data frame. It's pretty much the same story of a data frame. You can show, you can represent different types of data, which you can't in a plot. So that's another thing that you get from a table. Now, some best practices when you use a table to make it easier to follow, or visually more, make it easy to follow, make it easy to find things in a table. There are a couple of things we can do. These are the suggested best practices. Order columns based on the importance. Right? You start from some kind of index, something that is related to all these columns. Then try to put the most important columns at the beginning, or when you start from the left and go to right, start from the most important columns. So the order should somehow represent the importance. You can't put a specific column that is very important and it helps you tell your story or tell whatever you want to say or communicate, like as 10th column in a table. Keep it close. Start, the order should follow some kind of related to, should be a little kind of related to the how important that variable is. Use emphasis, like italic. Change the font for a specific variable in a table. Right? If you are representing variables in a table, something like this, you have so many variables, you know, represented numbers, you know, let me put here 10, 5, 20, 30, 50, 100, 0.8, 0.1, 0.6, and so on. Right? If you want to emphasize something, write that in italic, for instance. Let's say I want to emphasize this is specific, or maybe just some names, I should. Right? Let's say they're continent, like Africa, Asia, right? America, and you want to emphasize a specific continent, right? We can write it as italic. Write this as italic. You can change the font of something that you want to emphasize. Right? You can, instead of writing, when everything is written in normal font, you can write this 50 with a bold like font, right? Or a different font. Use color. Everything, let's say in this column is, everything is written in red, but you want to emphasize this number 50, so you can just write it in a different column. So now visually, when I look at it, I know that's something you want to emphasize. And if it's bold, I know it's something you want to emphasize. The last thing is obviously avoid excessive length column descriptive. If there's something you want to describe and it's too long, right, just use abbreviation and then explain that abbreviation in the table's caption. Don't use a very long sentence just to describe the column, like at the top as the column label. Or even within the table, right? When you have a type of data, in this case, it was continent's name, so it was pretty easy to put. But sometimes you end up having something long. Avoid using very long and excessive descriptions in tables. Now, 3 rules, and I really hope you follow these. Numerical data in a table should be right aligned. Right? So when you have a table, when you put the data in a table, a specific column, as I put it when I was giving you an example about scale representation, the numerical values, let's say this column is something that represents numerical values, they should be right aligned. So if this is 5, the next one is 100, it should be this way. The next one is 20 or 30, should be this way. The next one is 1,000, right? Should be this way. So all these should be, if you have a number or numeric column that represent numbers, they should be right aligned. If there is a text should be left aligned. Right? Again, like name of continent, right? They all should from the left, start from the left. Africa, Asia, America, going on, Europe. So text should be left aligned, numbers should be right aligned. This is for your reports. Obviously, when we do things in Python, NumPy, we don't really mind wherever the alignment is in that data frame, because that's not something that we are actually putting in a report. These are the general rules. When you put them in a report, you get the data and you want to submit a report, or you want to represent it in your presentation, you make slides. Now, following this rule, headers for the columns should align exactly the same way that the values in that column are aligned. So if you have a numerical set of values right here, the header for this should be right aligned, should be here. Header for the table that is left aligned, if it's text, should also be left aligned. And there is this strong suggestion: do not use center aligned at all in tables. So everything is either left aligned or right aligned. It's numeric, right aligned, categorical or text, left aligned. So three, I guess it was more than three, 4 things, right, to keep in mind when you are putting things in tables. Simplest kind of plot that you've seen a lot, you've dealt with that a lot. It's very common, dot and line plots. Right? We use that a lot in engineering. We usually represent a function defined by a set of points. Right? You have x values and then y as fx as a function of x, and you present that in, let's say, y-axis. Best practices. You have heard this multiple times, I'm sure. When you have data points, you have to show those data points. When you fit something on those data points, like you fit a line, you fit a polynomial, you have to show the data points along with whatever you fit. Now, you do not use lines, right? You use data points, like scatter plots, let's put it this way. You have points, and at the same time, you represent the fit. So do not just represent the fit. Data points should be there. So anyone knows how close the fit is, because, and the reason for that, the same fit can be for these data points or can be for these data points. So as someone who's looking at this, I need to know this, these data points. Visually, it helps to understand how things change. Show uncertainty in the data, right? Sometimes, for instance, you are drawing a plot and you are showing, let's say, the mean of some variable. You're showing, for instance, the mean of temperature. The mean value of temperature over different days of a week. So temperature and days. And you show the value by one number. This is, for instance, Monday, Tuesday, Wednesday, Thursday, you know, one number that you found the average for the day. Now you have to show the uncertainty in your data. Again, engineering is the same story. When you're measuring something, let's say you're averaging stress for an area, and they say in this part, the stress, the average was this much. You have to show the uncertainty. Sometimes it really matters in so many cases to show how did that variable change. You're giving me the average, right? In this case, temperature. How did that change? I know this is the average, but I'm pretty sure it was different in the morning from evening. And the reason you have to show that variation or uncertainty in your measurement, because it relates to the way that uncertainty specifically relates to the way that sensors measure variation. It gives us information. For instance, this average can be the average of 2 numbers that were here and here, or could be the average of 2 numbers that were here and here. I need to know, how did that vary? How did that change? And that's why it's important to show uncertainty. So many cases, not so many, but there are cases you don't have to use just one number, a specific number. You don't have to. Obviously, it depends on the type of data that you're representing. Usually they do it with a line showing that, at least from what I do, or the typical procedure is, you can show the standard deviation. For instance, you had a set of measurements. You measure the temperature 10 times during the Sunday or Monday. This is the average. Then you can show the value of the mean plus minus the standard deviation. All right? Plus the standard deviation minus the standard deviation. So it gives a sense of how was this variable changing. I will talk about box plots and whisker plots. Those are very good plots that they show exactly quartiles in a data distribution, like 25%, median, 75%, and then they show outliers that, oh, this specific data was very off from a mean value. We'll talk about them. Colors and different types of lines, you already know that. Use those to distinguish the lines, obviously. And if you have categorical data points, do not ever connect them. This is trying to say is that if you have some kind of categorical data like this, and they have nothing to do with each other, hopefully we get to talk about when we talk about bar charts, do not connect them like this and make a line plot, because they're not supposed to show the relationship. For instance, let's say you're working in a store, and this is the number of jeans that are sold. This is the number of, I don't know, shirts, specific type of shirts that are sold in one day. This is the number of something else, you know, shoes, a specific type of shoes that are sold in one day. Is, you know, you don't need to, you shouldn't connect these, because these have nothing, you're not showing, oh, the number of jeans increased, or the number of shirts increased with respect to number of jeans, right? Because just the data for one day, that doesn't make sense to just connect these together. You just have to use some kind of bar chart and show that specific point. So it's like a categorical data example. All right. Next type of plot is a scatter plot. Now they're used to represent a lot of data. When you have a lot of data points, I would say tens of thousands of data points for two variables like X and Y, or parameter 1 and parameter 2 in your data set. You use a scatter plot. You just throw them there. It's more like a dot plot, but now you have a lot of data with different, they change. Some best practices is very important to use the right size dots. What is the right size dot for a given data you have? Hard to tell. You are the best judge of that. So I'll show you an example. This is an example. This shows the BMI for, you know, distribution of Americans on the basis of BMI, height versus weight. You see the left one is way better than the right one. And why do I say that? Because there is a lot of data, and by using a big size data point, I'm losing the data here. I don't know how many data points are here. I can't see. They're so overlapping that they're creating an area that is pretty much just blue. I don't get the intensity of, or the way that each data point is related to each other, or get a sense of how much data do I have. Versus the left one is a good size, I would say dot, a good dot size, or the dots are, they do have a good size, because now I have a better sense that, well, see here, I have more data here, less data here, and I can see, I can get more information from this versus this one. So you have to think about, is it a good representation? Are those points overlapping too much so it's not really clear how many data points are there? So I have to keep that in mind. Second thing, clear that up. Do not use 3D scatter plots at all. This is a rule. There is only one exception to this rule, that in engineering, When you do scanning, like when you do laser scanning, for instance, you get a cloud, point cloud. Right? That is acceptable. No? A lot of time when we do scanning and you want to get a 3D vision of a surface, that's acceptable. We use 3D scatter plot because they show the points in a specifically, it's about the geometry XYZ, and we want to see the shape of that geometry. So do not plot 3 variables in a scatter plot. Doesn't really help. It's very hard to look at, and it doesn't really communicate well at all. Last thing, in case you have 3D data, you want to show more than 2 variables in a plot, use a bubble plot. Right? The bubble plot I was talking about when I was talking about different types of plots, and I said, well, when you have 2 variables, you want to make a comparison, use a scatter plot. You have 3 variables, you want to make a comparison, use a bubble plot. Bubble plot I'll show you a good example of that. This is actually the website Gapminder. So you're curious about visualizing different type of data, I'll encourage you to go there. That's pretty interesting set of data. Let's focus on life expectancy. Now, this is a bubble chart. Right? It shows the life expectancy versus income. Right? It's 2 variables, life expectancy versus income. Now, the third dimension in this data that they wanted to represent is the population. You see the size represent the population here. So if I hover my mouse over any of these data points, it tells me which country is that. Right? So this is China. The bubble, the data point is large because it has a huge population. Go somewhere smaller, like other countries. Somalia, right? It has, the population is lower, so the dot size is small. So now I have a third dimension. I can look at life expectancy versus income, and at the same time see how does that relate the population of each country. If the third dimension wasn't here, I just had a bunch of data points for each country. Right? It was just telling me what is the life expectancy for each country versus the income. Or where does each country stand, better to say, in with respect to life expectancy versus income. But now, with help using the third dimension, the size of the bubble, I can see also how does the population affect this. And this is for 2019, but we can go back and just take a look at the same thing for. So you have the third dimension. Don't use 3-dimensional scatter plot. Use a bubble plot. We'll talk about bubble plot and how to make them in Python. Hopefully, when we talk about advanced visualization. Next one is bar plot or pie chart. Any of these, we usually use this to represent the relative proportion of categorical variable. So what it does, well, basically partition a geometry, right? It's either a circle or a bar if it's stacked into areas proportional to how common that category is, or what is the size of the specific category, the variable related to a specific category we're trying to measure. Best practices. The first one is difficult to do. It's an old habit. As they say, old habits die hard. A lot of plotting softwares still don't do it. So no one is going to penalize you if you don't do it. But the best way or suggested way is to, instead of when you have a pie chart, for instance, and there are some sections in your pie chart representing different variables, like this one, this one, this one, depending on what is the portion of each variable, like this. What is it trying to say is that instead of saying 1, 2, 3, 4, 5, or using different colors and put labels here, one is a number of something, for instance, number of, again, go with that store, number of jeans sold, 2 is number of shirts sold. Instead of doing this, just put it directly on, I shouldn't have erased that. Just put it directly on the graph. So let's say this is the number of jeans. This is the number of shirts sold. Just put the title of number of products sold in one day. So that's what the first one is trying to say. Just directly put it on this slice. Second one, when you want to make a precise comparison, obviously use bar charts. Pie charts are hard to, it's a circle, unless you put the specific percentage underneath. It's visually easier, let's put it this way, to look at a bar chart. If I have a line there and I have my bar charts like this, right? It's visually easier to make this comparison between these things rather than a pie chart. A little bit, at least. It's suggested to use bar chart if you want to be very precise, because then y-axis you can give the numbers like absolute value. Pie chart tells us the percentage. It's hard to go with the absolute value, but bar charts you can put the absolute value and we can actually compare different categories. Last thing, highly suggested everywhere pretty much I've seen, never ever use 3D pie chart. You have seen it, the tools are available in different softwares to make 3D pie charts, but never ever use 3D pie chart. I'll share with you this article about why not. A very brief example. So the left one is 2-dimensional, the right one is pie chart in 3-dimensional. Never ever use 3D pie chart. Right? This, as they call it, chart junk. Nobody uses that or shouldn't use that because it defeats the purpose of a pie chart. In a pie chart, ads are popping off from here and there. A pie chart is I'll send you this article about the angle, about how it makes it confusing to see what portion of the data is a specific category when you put it in 3-dimensional space. And generally speaking, again, it defeats the whole purpose. We just want to see the relationship, and the easiest way to do it is in 2-dimensional flat. So whenever you see a 3D pie chart, tell that person that is a chart junk and should not be used. Pie chart is good enough when it's in 2 dimensions. Histogram. They are plots of the observed frequency distribution. We already know that, hopefully. And they are trying to answer a specific question, right? You have a set of data, you plot the distribution of that data, and you want to know where is the peak, how close the mode is to the mean. Right? You want to know a mode is most frequent data in your data set, mean is obviously the mean. So is the most frequent data is the average data, or it's kind of very far from the average data because you have some points that are so on the other side. If you think about the mean, you have some points that are so on the other side that are compensating for too many points or data points that are close together. Right? It gives us a sense of where the mode is and where the mean is, and whether the distribution is skewed or it's symmetric. Right? Where the mean is, whether it's very symmetric or it's skewed to one side or another. You're familiar with histogram plots, so I'll just give you two advice about best practices. The most challenging, one of the challenging thing about histograms is that you have to make sure that you use the appropriate number of bins. Those bins, number of bins that you divide the data. I mean, these are two examples. The number of bins, obviously I'm talking about how many subsection, or you want to say interval, you divide your data, right? So each of them is a bin. Right? How many bins you have for your data? This is very important in terms of visualization. In this case, I had a lot of data points here. This one. I had a lot of data points, so this is not a good presentation. Even this is not a good representation. Here is good. Now I'm getting to a smooth, like normal distribution. So this is a good number of bins for this data set. So you have to play around with number of bins to get the best representation of your data. The second row, if you look at it, This is, we have few number of, so this is a lot of data. This is few number of data points. And we decided to divide it into 7 bins. Now, if I increase the number of bins, you see what happens. Now I'm getting patterns that are not correct. These are, we have to have enough number of data points within each bin. If we split it more and more, we're going to get at some point that each bin probably has 1 or 2 data. And that is not what we want to represent. We want to represent the pattern in our data. We don't want to represent individual points because they don't matter that much. You know, what we need to know is how does this data change, and we want to see the distribution pattern. So in this case, these are not good representations. This is a good one. It gives me a relatively smooth representation of data distribution. But that's a tricky one, that you have to find a good number of bins when it comes to histograms. Last thing, it's suggested highly that use probability density function instead of just the histogram. Or better to say, instead of histogram that shows the number of occurrence of each event, use the probability, and that you can just do it by dividing the values by the whole number of events. Right? A good example here, put. So left one, right, they show the same exact pattern, right? But what happens is that if you look at the y-axis here, right, this is just the absolute value number. So it shows how frequent is 100. It's like 4 times in my data set. How frequent is, you know, some numbers around 99, whatever numbers we have in this bin. 7 happens 7 times. Instead of this, right, use density histogram. It's preferred because it tells us about the likelihood of something. So it tells us the likelihood of 100 or the data points around 100 occurring is this distribution, whatever series of events that happened and you measured, is about 0.04. The likelihood of values around here, right, it's pretty probable. Right? It's more close to 0.1. So use density histogram because, again, it suggests that it tells us better information compared to frequency histogram. It tells us about the likelihood directly. Well, you can easily do that by just dividing and scaling the whole thing by dividing it the whole number. All right, we'll talk about also histograms next class. All right, that takes me to the end of this.